So now I'm going to ask a couple of interesting questions, right? Even though it may seem a bit mathematical, I feel like it gives a special appreciation for these divergences and curls, right? So, like I said, that the divergence and curl interpretations using fluid flow does not quite lend itself directly in the case of electric and magnetic fields. There is another perspective that really puts a different light on the divergences and curls, right, and why they, these tend to show up in many physics equations, right. So let's take a look at this. So the first question I'm going to ask is, what is so special about these divergences and curls, right? So if you look at all the four Maxwell's equations, they are using these two gradient operations, right, divergence and curl, on vector fields E and B, right. The reason why this question is pertinent is, if I were to take a vector field V, right, which has components V1, V2, V3, I can define 9 partials, right. Right. So if I were to sort of combine these 9 possible derivatives, right, it seems like the divergence is only taking the diagonal elements, right. So if I were to, the divergence is essentially the sum of these three terms, right. So it's called the trace of the matrix, right. So the divergence is simply a scalar, right. Del dot V is dou V1 by dou x plus dou V2 by dou y and dou V3 by dou z, right. So divergence is essentially the sum of the diagonal elements, right. And what is the curl? It's actually this minus this, right. That is the third component of the curl. This minus this gives us the 2 component of the curl, and this minus this gives us the first component of the curl, right. So the question comes to us, what is so special about combining these this way, right. So I'm calling divergence, which is essentially the sum of these diagonal elements, and then I'm looking at these sort of antisymmetric differences, right, and I'm calling that a curl, right. Question is, what is so special about this particular combination of these 9 derivatives, right. So this is an interesting question to ask ourselves. So the divergence is the sum of diagonal elements, right, and then the curl takes the differences of off diagonal elements, right. So, in mathematics, especially when we are looking at tensors like this, right, of rank 2, there is an interesting property in mathematics, which is the trace or the sum of the diagonal elements does not change under similarity transformation, right. So, this is a very interesting property, right. So, if I were to translate my xyz axis, the trace of this does not change, right. So, that is a very interesting property of divergence, right. So, when I take the sum of the diagonal elements, it is independent of applying any similarity transformations. What this means is, even if I were to rotate the axis, right, I do not expect the value of this trace to change or the divergence to change, right. So, the divergence is invariant under similarity transformation. Right, it allows for rotation of the axis and the form of the equations do not change, right. This is extremely convenient, right. And then the curl, right, behaves like a vector, right. So, it transforms like a vector, and this is very convenient, right, because all physical quantities in physics we would like to express them using objects whose transformation properties are very well known, right. So, the statement that the curl transforms like a vector indicates a very special kind of transformation rule, right. It is a very special kind that says that regardless of the observer, right. So, we can say that the form for these physical laws or the Maxwell's equations does not change, right. So, the reason for the appearance of divergence and curl is actually quite deep, right, as it says that this particular form of writing the Maxwell's equations makes it invariant to similarity transformations, right. So, I can move around and rotate my coordinate axes, and I also know that the form of these equations will not change regardless of the observer, right. So, these are perhaps the reason why, the underlying reason as to why you see divergences and curls in the equation. Okay. So, we can say that physical laws become independent of observers. Right. But for those who are listening right now, the question is a deeper question happens, right, arises, which is are divergences and curls sufficient, right. So, we have 4 Maxwell's equations, and we have these equations transforming using divergences and curls. What is to say that there are not other combinations of these derivatives that may also be necessary, right. How is it that the divergence and curl is sufficient and that we do not need any other combinations of these derivatives to describe the electric and magnetic fields, right. And this is where we take recourse to a very special theorem by Helmholtz, right. Which says that if you specify in a volume, right, the divergence and the curl of the vector field, and if you specify the normal component of the curl along its surface, then the field is uniquely determined, right. So, this is a very powerful theorem by Helmholtz that says that just by providing divergences and curls of the vector field of interest in a particular volume, and if you specify the normal component of the curl on the surface, you can uniquely determine the vector field, right. So, we are not going to go into the depths of this theorem, right, but rest assured that mathematically there are proofs, right, that tell you that divergences and curls are sufficient in terms of uniquely determining the fields, right. Remember that electric and magnetic fields are something that physically exist, right, which means that there has to be one and one only unique solution to electric and magnetic fields, right. So, it is always important that whatever constraints we lay on the electric and magnetic fields, that it lends itself to a very unique solution to E and B, right. It should not matter who does the calculations, when the calculations are done, I should get the same results for E and B for a given scenario, right. So, given the divergence and curl and normal component of the curl on its surface, the field is uniquely determined. Right. So, this theorem perhaps gives you some satisfaction that perhaps divergences and curls are sufficient in order to uniquely determine our electric and magnetic fields. Okay. We are yet to show this. Okay. So, we will do this explicitly when we try to solve the Maxwell's equations. But before that, let us also inspire ourselves in getting a deeper meaning of what these divergences and curls do to the vector field, right, and map it to something that we may be familiar with, right. So, most students, when they start with vector calculus, it seems a bit daunting, right, lots of rigorous mathematics, lots of bookkeeping of these x, y's and z's, but one should not lose sight of the fact that what essentially these functions are allowing us to do, right. So, for this I am going to start with something very simple. Let us say I take this equation that operates on a scalar function f of x, right, and when I apply the derivative operator, I essentially get a scaled version of f of x, right. So, this is an eigenvalue equation where lambda is the eigenvalue and f of x is the eigenfunction, and the solution to this is of the form to within a constant, right, e to the lambda x. So, what can we say? E to the lambda x is the eigenfunction for the derivative operator, right, d by dx. Okay. So, now taking this to the vector gradients, right. So, let us start with right. So e to the I k dot r, right. So k is an arbitrary constant vector, right, and r indicates the vector for the spatial point x comma y comma z, right. You can say r is x ex plus y ey plus z ez, right, and k is some constant, arbitrary constant vector. You can write that as kx ex plus ky ey plus kz ez, right. So remember, k dot r is a scalar, right. It's just kxx plus kyy plus kzz, and e to the I times that is a scalar, right. So it is a scalar field, e to the I k dot r, and the reason for the, sorry, this I stands for square root of minus 1, right. So let's use j, that's what we are familiar with. So the reason to take j is I am looking at oscillatory functions. So when the gradient operator operates on this scalar function e to the j k dot r, we simply notice that this becomes j k e to the j k dot r, right. So what can you say? That e to the j k dot r is a eigenfunction for the gradient operator, right. So if you are still wondering how we got this, remember that del was dou by dou x times ex plus dou by dou y of ey and dou by dou z of ez, right. So if we do del of e to the j k dot r, this is just dou by dou x of e to the j k dot r ex plus dou by dou y e to the j k dot r ey plus dou by dou z e to the j k dot r ez, right. So remember, the exponent is just kxx plus kyy plus kzz. When I take the derivative, you will essentially get the corresponding component, right. So kx jkx would come out, and then you can remove the e to the j k dot r, right. So jkx e to the j k dot r, right. Kyy and kzz would be constant when I am taking the partial with respect to x, right. Plus jky e to the j k dot r ey plus jkz, right. I am kind of going through this because just getting some familiarity, right, with doing partials on such functions, right, using vectors and using the notation of vectors, applying derivatives on expressions and objects that contain vectors in dot product form or other forms, right. So these are some things that one needs to learn, but it should be straightforward, if you know basic calculus, you should be able to extrapolate to situations which involve vectors as well, right? So this is just the equivalent of saying this is jk e to the j k dot r. Okay. So this is interesting, right? So we notice that e to the j k dot r is the eigenfunction for the gradient operator. Right. So what is the physical meaning of this? So if I were to look at the function e to the j k dot r, right, and if I were to look at constant surfaces, right, just like our analogy for the elevation map, right. Remember I drew the the scalar field for elevation has contours of constant height, right. So if I were to ask a similar question, what are the surfaces, right, of the constant value for this scalar function e to the j k dot r. So that essentially yields to asking the question k dot r is constant, right, or kxx plus kyy plus kzz is constant, right, and that essentially yields planes in the three dimensions, right, and this k vector, right, which is the eigenvalue, is essentially pointing normal to these surfaces, right. So if you remember that the gradient of the scalar function I said was the direction of the steepest ascent, right. So similarly here, when I applied the gradient operator, I am essentially getting the direction that is normal to the constant surfaces, right. So there we said that the direction would be normal to the tangent along the contour line that we drew in the elevation map. Here, since the dimension has gone up, this is a three-dimensional scalar field, we notice that these are constant surface planes, right, and the k vector is normal to these surface planes. Okay, so this is, but simply written in English, that the gradient is normal to its level surfaces. Okay, so we are seeing an interesting property of the gradient. We will see a little bit more. Now we will bring in a vector field, right. So A and K are arbitrary vectors, arbitrary but constant, right. I can choose what I like for A and K, and remember this is a vector field. Right. So A is a vector, it's an arbitrary constant vector, and e to the j k dot r, like we saw in the previous example, is a scalar, and we are just multiplying this constant vector by a scalar at every location, right. So this is a vector field. Now when I apply the divergence, right, so the gradient can operate in two ways with vector fields. One is the divergence and the other is the curl. When we look at the divergence of this vector field, what do we get? So I'll let you do this exercise. Please try to pen this down on a piece of paper, right, so that you get used to dealing with derivatives, vectors, right, and vectors being operated with gradients and so on, right. You essentially find out that this just becomes jk dot okay. Remember, this is a scalar, right. A e to the j k dot r is a vector field that, when taken dot product with k, will give you a scalar, right. So this is very fascinating. So if we also do the curl of the same vector field, you can check this again. That you essentially get jk cross a e to the jk dot r, right. So the del dot and the del cross, right, these operators, when operating on this vector field a e to the jk dot r, is essentially giving us jk dot the vector field itself, or jk cross the vector field itself, right. So we can say that a e to the jk dot r are eigenfunctions of the divergence and curl operators, right. So we are able to convert divergences and curls into constants, right, on the right hand side. So what is this trick that is very popularly used? So you should be thinking of the times when you were solving circuits, right, and they probably introduced the idea of Fourier transform or the Laplace transform, right, where you converted the dou by dou t's or the d by dt's into j omega, right. So this trick where you take derivative operators and convert them into variables or algebraic numbers is Fourier analysis, right. Okay. Remember that on the left hand side I have del dot and del cross, and on the right hand side I just have vector dot products and vector cross products, right. So differential equations are converted to algebraic equations. So this is the stepping stone of trying to say that I can take an arbitrary vector field, right, and I can of course split it using the Fourier analysis into individual components, right. So if you remember back in the signals and systems, you can take any signal in time domain and decompose it into individual Fourier coefficients, right, which indicate how much of every frequency is contained within the signal. Similarly, I can take an arbitrary vector field in R and decompose it into these vector fields of the form a e to the jk dot r, right. And for each of these vector fields, the del dot and del cross is essentially translating into algebraic equations, and since the Maxwell's equations are linear, right, I can simply superpose all these individual equations in order to get the net field, right. So, I can have these Maxwell's equations operating on these eigenfunctions, and I have converted the Maxwell's equations into algebraic equations, and I can do so looking at these algebraic equations for every Fourier component of the field, right. So, this is a very elegant method, right, a mathematical way for us to be able to handle vector fields, right, and uniquely determine them, and to be able to solve these vector differential equations. We take advantage of the fact that these divergences and curls have these very convenient eigenfunctions, right, and these eigenfunctions can be used repetitively in a linear weighted sum form to represent any field of any type, right. So, an arbitrary vector field in R can be expanded in the Fourier basis right, and since Maxwell's equations are linear, I can superpose the equations for each component and reconstruct the field. Okay. In my mind, this ability that the divergence and curl lends us is perhaps more exciting, right, than having to create a physical interpretation of divergences and curls in our minds, right. I believe that the meaning of having divergences and curls in the Maxwell's equations runs quite deep, right. For one, we saw that the divergences and curls lends itself such that the Maxwell's equations become form invariant, right. So, regardless of rotations of these axes, regardless of the observer, the Maxwell's equations maintain its form, right. So, that the divergences and curl give this special unique property to these Maxwell's equations, and we are also noting that these divergences and curls have very convenient eigenfunctions, right, that I can take an arbitrary vector field and I can decompose it using the Fourier analysis, and I can use the Maxwell's equations sequentially on each of these components, right, and then do a linear sum, right, to extract the entire field. I believe that these advantages, right, are extremely important and is really the source of how we are able to tackle something this complex quite easily in our day-to-day lives, right. This in fact is the stepping stones for the evolution of commercial softwares that are able to now solve Maxwell's equations for you quite readily, right. So, the strength of the mathematical foundation that we have laid using these divergences and curls really allow us to be able to express any field type, right. So, electric and magnetic fields in any scenario with any distribution of currents and charges, we are able to use these set of equations and we are able to reconstruct the field uniquely in every given situation. Again, I am kind of refreshing the thought that the reason I call Maxwell's equations linear is, remember, there are no expressions that involve the quadratic or the cubic, no exponent of the individual field components. We don't have Ex squared, Ex cubed, or Bx squared, Bx cubed. Any component of the field is not raised to any power, nor their derivatives, right? Spatial or temporal derivatives. You can have first order derivatives, second order derivatives, but we don't have dB by dt whole square, or we don't have dE by dx whole square, right? So since we don't have these equations containing any object that is raised to some power, we call the Maxwell's equations as linear equations, right? So Maxwell's equations are linear. We can't call them homogeneous yet. Some of them are. We'll look into it in the next week, where I introduce the Maxwell's equations, and we'll go about solving the 4 sets of Maxwell's equations. But I would like to leave this week, right, with this thought in mind, that all the mathematics that we prepped up for is really to enjoy the rigidity that these Maxwell's equations provide us, right? And you are also getting some deeper insights into why these equations are the way they are, right? So finally, I'd like to say that the divergence equations, right, essentially give you the component of the vector field that is aligned to the direction of choice, right. So remember, del dot a e to the j k dot r was j k dot a e to the j k dot r, right. So remember the dot product and its definition. We are essentially taking the vector field and we are asking how much of the vector field is aligned in the direction of k, right. So for an arbitrary choice of k that you pick, right, the gradient by the means of divergence, right. So del dot of this vector field essentially tells me how much of the vector field is aligned towards this arbitrary direction that you have picked, right. And what does the curl do? Remember, k cross the vector field is a vector that is perpendicular to k, right. So it's essentially telling you the tangential or the normal direction, right, the transverse component of the field to the direction that you have picked, okay. So the curl equation essentially gives you how much of the vector field is in the transverse direction to the direction that you have picked, right, the k vector direction. Right. So in some sense, the divergence gives you the longitudinal component and the curl gives you the transverse component, and together you can get the net field, right. So, I will probably conclude this week's lectures, which is essentially supposed to give you the basics and introduction to vectors, gradients, and how these gradients operate on vector fields and scalar fields. And then we also looked at how the Maxwell's equations, which were originally expressed in the integral form, can be converted to a point form or a differential form. And we also looked at why the Maxwell's equations only seem to be using divergences and curls. We summarized by saying that divergences and curls have very special transformation properties that allows for the Maxwell's equations to be form invariant and also allow for similarity transformations, right. So, I am able to do this in any basis, any of the coordinate systems I choose. The form of the Maxwell's equations remain the same no matter what observer is looking at the fields. The Maxwell's equations remain the same, and we also notice that the divergences and curls have a special property on that if we were to decompose any vector field into its Fourier basis, the divergences and curls essentially reveal the longitudinal and transverse components, and these, when I can take the linear sum of it, because the Maxwell's equations are linear themselves, can give you the full picture and can tell you that the fields can be extracted, right, from the Maxwell's equations. Now it is up to us to also convince ourselves that the Maxwell's equations also lends unique solutions, right. So, remember, all our discussions so far has not yet talked or touched upon uniqueness of the solutions that come out of Maxwell's equations. We have just seen that divergences and curls lends to a certain versatility to the Maxwell's equations, that we are able to apply the same set of equations in different scenarios, right. And it also helps us to use Fourier basis and Fourier analysis that we are very used to in order to reconstruct any field in any situation there may be, right. Thank you.